Friends, good morning to everyone. Today's subject of discussion is protecting groups. In precise, we are going to deal with protection of 1,2 and 1,3 diols. The 1,2 diols can be protected by treating with a ketone. In general, we can use acetone. The R3 and R4 here is methyl group. The OH has lone pair of electrons and the carbonyl carbon is a positive center. The lone pair of electrons are shared with the carbonyl carbon and pi electrons moves onto the oxygen and this it becomes O minus and it combines with H plus to form a bond between carbon and oxygen. In the presence of acid, the OH becomes protonated over here and make this carbon more positive. This electrons moves towards oxygen to satisfy the positive center. Onto this positive center, lone pair of electrons from the adjacent hydroxy group attacks on it and H2O gets kicked off and it gives rise to corresponding acetonides or isopropylidines. In other words, they are protected in the form of isopropylidines, which are also called as acetonides. Generally, a ketone is used. The ketone generally used is acetone. If there are two carbon groups between the two OH groups, then it is 1,2 acetonide is formed. If it is separated by three carbons, the 1,3 acetonides are formed. 1,2 acetonides are generally more easier to form than that of 1,3 acetonides. This can be attributed to the fact of nearness of the two OH group in case of 1,2 diols. They can be cleaved easily by using mild aqueous acid, that is HCl or H2SO4 in the diluted form. They can also be protected in the form of cycloalkylidins. Instead of acetone over here, we can take cyclopentanone. Similar to that of the formation of acetonide, the OH group lone pair of electrons forms bond with the carbonyl carbon, making the pi electrons to move on to the oxygen, which becomes OH. And another OH group oxygen lone pair of electrons attacks on the carbon and OH gets kicked off as water molecule. The same can be achieved by using cyclohexanone. We can either use cyclopentanone or cyclohexanone in the presence of an acid. It loses the water molecule and it can form either cyclopentylidine or cyclohexylidine depending upon the reagent which we use. Cyclopentylidines are slightly easier to cleave when compared to that of acetonides which are formed, which has been shown in the previous reaction over here. Cyclohexylidines are little difficult to get cleaved than that of acetonides. These are the salient features of protection in the form of cycloalkylidines and that is cyclopentylidines and cyclohexylidines. They can be also cleaved by using mild aqueous acids. 1,2 diols and 1,3 diols can be protected in the form of benzylidines. To form benzylidines, instead of using cyclopentanone or acetone, we use here benzaldehyde. The lone pair electrons present on the oxygen of the OH group is shared with the carbonyl carbon in the presence of an acid, and the pi electrons moves onto oxygen making it OH, and in the presence of acid OH gets protonated OH2. That's why it makes it positive center. To satisfy the positive, the electrons moves onto oxygen, and that gives away as water molecule. And on this carbon, the positive carbon, the electrons gets attached, and OH moves as H2O, and we'll get the benzylidines. The two OH groups at 1,2 position or at 1,3 positions can be protected from the further reactions. 1,3 benzylidines are more easily formed than that of 1,2 benzylidines, whereas in case of acetonides, 1,2 acetonides are more easily formed than 1,3 benzylidines. This is the salient feature of benzylidine. Whenever 1,3 benzylidines we need, or 1,3 diols to be protected, we use benzylidine route. They can be easily hydrogenalized. Hydrogenolysis of benzylidines leads to cleaving, and we can recover the corresponding diols. But however, the hydrogenolysis will be slower when compared to that of benzyl ethers or olefins. They can be cleaved by acid hydrolysis similar to that of cycloalkylidines and acetonides. Another method of cleaving the benzylidines is by using hydrogen. We can carry out lysis. That's why it can carry out. We can carry out hydrogenolysis. Instead of benzylidines, we can protect in the form of paramethoxybenzylidines by treating the diols with corresponding paramethoxybenzaldehyde in the presence of an acid. Similar reaction takes place. The OH electrons are shared with the carbonyl carbon, making the pi electrons move onto the oxygen, which becomes OH, and the lone pair of electrons available in the adjacent oxygen of the OH group attacks on the carbon, and OH minus gets kicked off, which combines with H plus of the acid and loses water molecule to give rise to paramethoxybenzylidine. They can be cleaved more easily than that of benzylidines. The rate of cleavage hydrolysis is 10 times more faster than that of benzylidines. That's why when we want easy cleavage, we go for protecting the diols in the form of paramethoxybenzylidines. They can be cleaved oxidatively by using ceric ammonium nitrate. CAN stands for ceric ammonium nitrate. Another method of protecting the diols is in the form of carbonates. A diol we take and we treat with phosgene or carbonyl dichloride. As phosgene is not environmental friendly, we can use an environmental friendly reagent also. The carbonyl carbon is the positive center, and these electrons on the oxygen of the OH is shared with the carbonyl carbon, and chlorine is an easy leaving group. That's why chlorine gets removed. The adjacent hydroxy group oxygen lone pair of electrons are shared with the carbonyl carbon, and the chlorine gets removed, and it gives rise to corresponding carbonates. Instead of carbonyl dichloride, we can also use carbonyl diimidazole, which is more environmental friendly, and we get corresponding carbonates. And hence 1,2 diols and 1,3 diols can be protected in the form of carbonates. These carbonates are stable to acidic condition and they are more difficult to hydrolyze than that of esters. As we know, it can be formed by using phosgene or triphosgene, or it can be replaced by the carbonyl diimidazole, which is more eco-friendly. As they are stable to acids, they can be hydrolyzed by using the bases. Summarizing everything, the 1,2-diols and 1,3-diols can be protected as isopropylidines by using the protecting reagent acetone, and 1,2-acetonides are more easily formed over 1,3-acetonides. This stands as the salient feature of isopropylidines, and they can be deprotected easily by using mild aqueous acid, that is HCl or H2SO4 in the dilute form. Cycloalkylidins as the another way of protection of the 1,2 and 1,3 diols. The protecting reagents used is cyclopentanone and cyclohexanone. They can be cleaved easily by using mild aqueous acid in the similar fashion of isopropylidins. The salient feature of this cycloalkylidins is that cyclopentalidins are more easily cleaved than that of acetonides, and cyclohexylidine requires more stringent conditions when compared to that of acetonides. They are also protected by the form of benzylidins by using the protecting reagent benzaldehyde, and they can be hydrolyzed easily by using acid hydrolysis like that of isopropylidins and cycloalkylidins. Another method of cleaving the benzylidins is hydrogenolysis. Lysis by using the hydrogen. In case of isopropylidins, 1,2-acetonides are more easily formed, whereas in case of benzylidins, 1,3-benzylidins are more easily formed when compared to 1,2-benzylidins. The hydrogenolysis can be used for cleaving, but however, the hydrogenolysis rate is comparably slower than that of benzyl ethers and olefins. Paramethoxybenzylidins is another way of protecting the diols by using the protecting reagent anisaldehyde. The beauty of this paramethoxybenzylidins is the fact that hydrolysis is 10 times faster than benzylidins, and it can also be cleaved by using oxidative cleavage. Acid hydrolysis is the method of cleavage similar to that of all the others, and it can be oxidatively cleaved by using ceric ammonium nitrate as the oxidizing agent. The fifth method of protecting the diols is in the form of carbonates by using the protecting reagent phosgene or the more eco-friendly 1,1 carbonyl diimidazole, and this is stable to acid and thus more difficult to hydrolyze. Here you see all the other protecting groups or other types of protection, they are cleaved by mild aqueous acids, but here as they are stable to acids, they are cleaved by using the bases like sodium hydroxide and so on. Totally, there are 5 methods of protecting the diols by using 5 different reagents. The salient features have been mentioned here in each method, and the deprotecting agents what they have been used has been mentioned here. There are totally summarizing everything. There are 5 methods of protection of diols, and I have mentioned the protecting reagent and the deprotecting agent and their salient features. Hope you have understood the concepts well, and in the next presentation let us deal with the protection of other functional groups. Till then, have a nice day. Thank you.